In this video, I am going to discuss the various logic gates and their use cases. First, we have the NOT gate. This gate takes in a single digital signal and simply inverts it, meaning if the input is a high voltage, the output is a low voltage, and vice versa. Representing these signals in binary form, if the input is 1, the output is 0, and if the input is 0, the output is 1. In digital circuits, there are many instances where you want to invert the state of a signal, and this is a classic application for NOT gates. AND gate. This one takes in 2 or more digital signals. This is the same for all the other gates that I am going to talk about in this video. The output is high if and only if all the signal inputs are high. Otherwise, the output is low. This means that if any one of the inputs to an AND gate is a low voltage, then the output is low. AND gates are commonly used to transmit data when only certain conditions are met. For instance, the state of B can only be transmitted to the output if condition A is met. NAND gate. This is simply an AND gate connected in series with a NOT gate. Take note that this is only an analogy and not how the circuitry is actually wired inside. What this means is that it does the opposite of an AND gate, since its output is being inverted. So, the output of a NAND gate is a low voltage only if all the input signals are high. Otherwise, the output is a high voltage. NAND gates are widely used because they are simple to produce and can be used to create any other type of logic gate through clever combinations. This versatility makes them cost-effective and popular in digital circuit design. OR gate. The OR gate produces a low output voltage only if all the input signals are low. That means if any one of the input signals is a high voltage, then the output will be high. The OR gate is most commonly used in situations that require action to be taken based on a number of signals, and any one of these signals can trigger the action. NOR gate. This can be imagined as an OR gate in series with a NOT gate. This means that the NOR gate is the opposite of the OR gate. Thus, its output is high only when all inputs are low voltages. If any one of the inputs is high, the output is low. The exclusive OR gate. This logic gate only produces a high output if an odd number of input signals are high. What this means is that the output of an exclusive OR gate is high if either 1 or 3 or 5 or any other odd number of all the input signals are high. The common misconception with this gate is that if all the inputs are high, then the output must be low. This is only the case for an even input exclusive OR gate. If the total number of inputs is odd, then the output is also high whenever all the inputs are high, because then we will be having an odd number of high inputs, which is the defining condition for this particular gate. Exclusive OR gates are useful in checking the parity of a binary word, meaning a test to see whether a string of bits has an odd number of ones or not. Even parity has an even number of ones in the binary word, and this will result in a low output when the word is passed through an exclusive OR gate. Odd parity has an odd number of ones, and this yields a high output on an exclusive OR gate. Parity checks are highly useful in data transmission to check for errors in transmitted data. More on this in a later video. Exclusive OR gates are also highly useful in creating a binary inverter, which is a digital circuit designed to flip all the bits in a binary word. Exclusive NOR gate. This can be visualized as an exclusive OR gate in series with a NOT gate. Thus, the two are opposites of each other. The exclusive NOR gate yields a high output if there are no high inputs or if there is an even number of high inputs. Otherwise, the output is low. Simply put, this means that it produces a high output for even parity binary words and a low output for odd parity binary words. The most common application of exclusive NOR gates is in bit comparison. Consider an exclusive NOR gate that takes in 2 inputs. According to the rules we have established for this gate, its output is high if the inputs are similar, so the output can be used to check whether the bits have the same states or not. I will go into the details of how to implement some of these circuits, such as the binary word inverter, parity checking, and the binary word comparator, in a later video. If you enjoyed the video, please leave a comment, hit that like button, and consider subscribing to the channel so that you never miss any new videos. That's it for now. Thank you for watching.